In this video we are going to look at the binomial distribution. So the binomial distribution is something we can use to model and find probabilities in certain situations. So we can use the binomial distribution when there are a fixed number of trials. So we've got a value n which is fixed. We are talking about two possible outcomes which we're going to refer to as success and failure. There is a fixed probability of success, so no matter how many trials we do, that probability of success stays the same. And finally, trials are independent of each other, so that just means that the effect of one trial does not have an impact on what happens on the next trials. So we define the random variable x to represent the number of successful trials. So x is the number of successful trials. We can write x follows a binomial distribution with the number of trials n and probability p. Now, this is notation we're going to see quite a lot of. So I want us to consider the following situation. So we've got a box containing 4 pens. We've got one black, one red, one green and one pink. And we want to use the binomial distribution to model the probability for the number of pens that are working. So we're interested in how many pens in our box are working. So if I think about the number of ways in which I can have each number of pens working. For no pens working, there's only one possibility. None of them work and all 4 don't work. There's only one possibility there. When I have one pen working, well, there are 4 different possibilities. Either the blue one or either the black one works and the other 3 don't, or the red one works and the others don't, or the green works, or the pink works. So there are 4 different possibilities there. When there are 2 pens working, well, all the possible pairs, black with red, black with green, black with pink, red with green, red with pink, green with pink. And equally, the corresponding pairs don't work. So when black and red do, green and pink don't, and so on. In either case, there are 6 different possibilities there. For 3 of those working, that's kind of the reverse of this here. If 3 work, there's only 1 that doesn't, so that is kind of just mapped onto what's there. So 4 possibilities, and equally for all 4 pens working, there's only 1 possible outcome, and that's that they all work and that there's none that don't work. So if I look at those values I have there, 1, 4, 6, 4, 1. Hopefully those values are familiar to us. They are a set of values from Pascal's triangle, because in the row of Pascal's triangle containing 4, since we had 4 pens, we may recognise that 1 is 4C0, 4 is the same as 4C1, 6 is the same as 4C2, and so on. 4C3, 4C4. So we can recognise the connection to the binomial expansion, which is why this distribution has its name, the binomial distribution. So if x follows a binomial distribution with a given number of trials and a given probability, then its probability mass function is given by, now this equation looks fairly complicated, but if we break it down, we can see that this term here just represents a value from Pascal's triangle. For example, that might be 4C1 or 4C2. So this term is just from Pascal's triangle. We've got P, which was the probability of success, to the power of the number of successes. Since we're talking about x being equal to r, and we said x was the random variable representing the number of successful trials, so that's the probability of success to the power of the number of successes multiplied by 1 minus p must be the probability of failure, since p was the probability of success, to the power of the number of failures. If there were r successes, there must be n minus r failures. So we've got a number from Pascal's triangle, the probability of success to the power of the number of successes, the probability of failure to the power of the number of failures. And that's how we're going to work out our probabilities. So, our first example. We're told a box of pens, that same box contains 4 pens. The probability that each pen works is 0.8. And we're being asked to find the probability that 3 of those pens work, that exactly 3 of those pens work. So first of all, and always in these questions, the first thing we can do is write it in the notation we're used to seeing for a binomial distribution. So we've got x following a binomial distribution where there are 4 trials, since we've got 4 pens, and the probability of success is 0.8. We're going to consider the success, meaning that our pen is working. So the probability that x equals 3, that's the probability that we've got 3 pens working, is equal to 4c3, since we're interested in 3 pens working out of 4, times the probability of success, 0.8, to the power of the number of successes, well, we want 3, times the probability of failure, 0.2, to the power of the number of failures. And if there were 3 successes out of 4 trials, there must have been 1 failure. So these are just values we can put into our calculator. I can use my combination function on my calculator to find 4c3. I can work out each of these, and when I put that into my calculator, that is going to give us 0.4096. So that there is our answer. Our next example, we're told Sergio rolls a fair 6-sided dice 10 times. Find the probability he rolls exactly 3 6s. So again, we've got x following a binomial distribution where the number of trials is 10 and the probability of success is 1/6. We're interested in how many 6s he rolls, and on a fair 6-sided dice, that probability is 1 out of 6. So the probability that he rolls exactly 3 6s, the probability that x is equal to 3, is going to be equal to 10c3 times the probability of success, which was 1/6, to the power of the number of successes, which is 3, multiplied by the probability of failure, which is 5/6 to the power of the number of failures. So that there is 7. And again, I can put that into the calculator just to demonstrate on this one. We've got 10c3 times by 1/6 to the power of 3 times by 5/6 to the power of 7, and that is going to give us our answer of 0.1550. So 0.1550. Our final examples. The random variable x follows a binomial distribution with a number of trials 12 and a probability of 1/6. So the probability that x equals 2, probability that x is equal to 2 is equal to 12c2 multiplied by 1/6 to the power of 2 multiplied by 5/6 to the power of 10. Since there were 2 successes, there must be 10 failures if there were 12 trials. And that gives us, when we put it into our calculator, 0.2961. The probability that x is equal to 9 that is equal to 12C9 times probability of success 1/6 to the power of 9 times 5/6 probability of failure to the power of 3. And again, if there were 9 successes out of 12 trials, there must be 3 failures. And when I put that into my calculator, it's going to give me 0.00000126. A very small probability, but logically that makes sense, because if we think about this binomial distribution, our probability of 1/6 is the probability of rolling a 6 on a dice. So if I'm rolling a dice 12 times, the probability of me getting 9 6s out of those 12 is going to be very low. So this value, while it is a very small number, it does make sense. The last question we're going to look at, the probability that x is less than or equal to 1. So slightly different here, we've got less than or equal to 1. Now in a future video, we're going to look at situations where we have less than or equal to, or some other inequalities appearing, where the method we're going to use now would be quite long-winded and would take a long time. On this though, since it's less than or equal to 1, the possibilities are either that the probability of x being equal to 0 is what we're finding, because we either have 0 successes or we have 1 success. They are the 2 possibilities. So the probability that x is equal to 0 is 12C0 times 1/6 to the 0 times 5/6 to the 12. The probability that x is equal to 1 is 12C1 times 1/6 to the 1 times 5/6 to the power of 11. And then we could either work these two out separately or just put them together just like this into our calculator. And that is going to give us 0.3813. And that's our final answer on that last question there. That's the end of this video. Thank you so much for watching. For more A-Level and GCSE maths content, like and subscribe to N Jackson Maths on YouTube.